Part 2 of our titration graphs focuses on conductivity curves. So when sodium hydroxide is added to a solution of hydrochloric acid, what we're finding is happening is the hydrogen ions are reacting with the water ions, and instead of being replaced by the sodium ions, and a sodium chloride solution will be formed. So as that reaction is taking place, the concentration of the hydrogen ions are decreasing, and you'll see this in the graph, and we'll see that the graph will actually decrease also in conductivity as that reaction occurs. And we can see in this equation just below here, we can see those ions in solution. We've got our sodium hydroxide reacting here as our base, and we've got our acid here. Now when they go into the reaction vessel, obviously they're going to dissociate, and because it is a neutralization reaction, we're going to get our formation of our water, as we can see over here, and the remaining stay in solution in their ion form. So some things that we do know is that our our hydrogen ions and our OH ions, so let's make that AH plus, ions move faster in the solution than our sodium and our chloride. So while there is a greater presence of those hydrogen ions, our conductivity is going to be higher. As that gets used up in the formation of water, we're going to have an increase in the sodium and the chloride ions, and that's going to reduce our conductivity. So conductivity does depend on a couple of things, and they're listed here: the identity of the ions, so which ones are there, the charge, what charge they have, how much of them are there, and the temperature of the solution as well. So let's look at a couple of different graphs for each of the scenarios that we've been looking at so far. So here we have a strong acid, strong base solution. Now we have an initial, we can see here its conductivity, and we can see the volume of sodium hydroxide that's been added. So we start off with a fairly high conductivity up here. And that again is because we have our acid in solution, and it's a strong acid which totally dissociates. So we're going to have, a greater concentration of those hydrogen ions. So we have that high initial conductivity. But as we're adding more and more hydroxide, so we're adding the hydroxide ions here with our sodium hydroxide. As I'm adding those, my water is being formed. By my water being formed, I'm also making sodium chloride. Those sodium and chloride ions are not as conductive as the hydrogen and the hydroxide, so we're finding we're getting our conductivity decreasing. Now this point here on our graph is our equivalence point, the point where the hydrogen ions equal in concentration our hydroxide ions. And that's always indicative there with our equivalence point with the lowest conductivity. Now after equivalence, what's happening here is I have got excess OH now. I'm just adding more and more and more hydroxide ions. There's no more hydrogen ions to bond with those hydroxide ions, so I'm not forming any more water, so I'm increasing that concentration then of my hydroxide ions, which again are higher in conductivity. So if we have a look at another example now, and we've got now a strong acid and a weak base. So again, we're at the same starting point where we've got a strong acid with high conductivity up here. And again, that's just due to the full ionization of those ions. Again, our conductivity is going to decrease. So as I'm adding, in this case, we can see here my weak base is ammonia. As I'm adding some ammonia, the concentration of my hydrogen ions is decreasing because that hydrogen ion is bonding here with our NH3 and producing an NH4 plus, which again, relative to the hydrogen, is lowering conductivity, so it's going to decrease there. Again, we can see our equivalence point just here, which indicates obviously that equivalence point where the hydrogen ions equals our hydroxide ions. Now, if we continue to add more and more NH3, it's a really weak acid, weak base. So by adding any more of that there, it's only dissociates to a very small extent. So there's not many of those ions there. So the conductivity is not going to increase. Now here we kind of have the opposite thing happening. We're starting with a weak acid. So as we know, they don't ionize fully, so it's only a partial ionization. So you can see therefore there's not many hydrogen ions in solution, so therefore the conductivity is fairly low. As I'm adding some sodium hydroxide, what's happening is we're getting a reaction occurring. So you can see here the acid that we've got is acetic acid and our strong base. So what's going to happen is my acetic acid is going to donate that hydrogen to the OH and make water, and so I'm going to be left then with a CH3COOH, COO minus ion, and then some sodium ions. Now our sodium ions are not particularly conductive. Our CH3COO ions a little bit more, but past this point we are now getting excess in the OH, so we're definitely going to see that increase there. And finally, our example is a weak acid, weak base. So again, the conductivity is low due to that partial dissociation of our acid. Now what's happening is we're adding our weak base again, our ammonia. So again, I'm getting that formation of the CH3, and don't mind my error here with my typo, CH3, get rid of that one, OO minus ions, which are a little bit more conductive. So it's going to increase there in terms of conductivity, and again, that equivalence point, it's going to plateau off there a little, also because of the conductivity not being particularly great once that weak base is in excess. Again, like with our titration curves, we're going to practice a lot of these questions in class, and I'm sure it'll make a lot more sense when we have a practical example in front of us. I'll see you then.